Okay, so let me introduce the FAMES pilot line. So as you probably know, the European Chips Act led to an initiative building 5 pilot lines. So led by IMEC, Fraunhofer, CEA, ICFO, and CNR in Italy. Actually, CEA, we are a partner of the 5 pilot lines, and we are the coordinator of the FAMES pilot line for FDSOI and applications. And I will present today this particular FAMES pilot line. So in one slide, let's see the consortium and the budget. So it's a consortium of 11 partners with 4 hosting sites. So we make a distinction between hosting sites and the other partner. Hosting site mean that this partner, VTT, Tyndall, Silicon Austria Lab, and CEA-Leti, receive CapEx. So that means that the pilot line will be distributed over those 4 countries. And the other countries are partners for the R&D program, because the pilot line is also a huge R&D program to prepare technology for the future. So as you can see, it's not a normal EU project. It's a huge EU project with more than 800 million euro funding. Half of the funding comes from the CHIPS EU, from EU, and half of the funding comes from member states. And what is very particular to this project too is that there's almost 50% of the budget is for CapEx, which is quite unusual for EU projects. With this, the aim of the pilot line is to build up a semiconductor pilot line in Europe for advanced technology, with an aim to provide opportunities for disruptive chip architectures by developing new FDSOI nodes and technologies around that could be used with FDSOI. And of course, the global aim is to strengthen European leadership. I don't know if we can say we have a leadership in advanced semiconductors, but at least try and be more leader than we are today on this area. From the beginning, we received a great support from industry. So 44 companies provide letters of support from Europe, from US, from Japan, meaning that these companies are quite interesting in the project itself and would like to see the results and to know more about the results, so that to see how they could leverage this result for their own programs. But at this stage, it was just a letter of support. They are not directly involved in the project. As you know, industry is not could not be partner of the consortium of the pilot line at this stage. So what are we doing in the pilot line? We will focus on a bunch of technologies. First, the heart of the FAMES pilot line is to develop FDSOI new nodes. FDSOI, as you know, is a technology that has been created in CEA in Grenoble and heavily patented. So we try to continue the roadmap on this technology, but we also work on a number of additional technologies, such as embedded NVMs, RF components, 3D integration with 2 ways of doing 3D integration, and small inductors. So I will give one slide for each of these technologies, just to give an overview of what will be done in the FAMES pilot line. And we have a full work package on eco-innovation. As we know, this is a growing concern for the industry, for the semiconductor area, and a growing concern in Europe, to work on eco-innovation systems, processes, new materials, how to reduce energy, use of water, and all these topics are very important for the future of semiconductor industry. In the end, we build a program, the FAMES program, around FDSOI, because we believe this technology has a very good, let's say, interesting advantage regarding the trade-off of power, performance, area, and cost, And also more and more, we are not only talking about PPAC, but also PPACE, because the environmental impact is a part of the trade-off today. And FD-SOI, we assembled this slide a few weeks ago. We already in 2025 have more than 100 products on the market based on FD-SOI technology in various fields like wireless communication, automotive, computing, aerospace, quantum technologies. You see it's a bit small, but you see the companies, even big names, American fabless such as Qualcomm, Samsung, who is actually manufacturing also its own circuits in FD-SOI, are involved in the development of these products. So regarding the technology, first, as I said, we will develop 2 new generation of FD-SOI components to improve the density of transistors because this technology offer a very good trade-off between high performance and low power. This is thanks to the 4-pin, as you can see on the scheme. It's not a let's say normal transistor. We have this 4-pin, the back bias, by applying some current, some tension on this pin. We can monitor to have more performance or low power circuits. Moreover, SOI technologies is a good candidate for radiation resistance, which can find some interest in specific applications such as defense and spatial applications. And the manufacturing costs are also lower. I mean, the masks are a little bit higher, but you have less steps and it's planar technology, so it's easier to manufacture. As I said before, it's heavily patented by CEA-Leti. And then we have a number of technology we are going to develop in the pilot line, non-volatile memories, embedded memories that are very good performance because they are reprogrammable and erasable multiple times, and low power consumption. We work on a bunch of different technology like AUX-RAM, magnetic RAM, FIRAM, FIFETs. And if I go back 3 slides, you see that this embedded non-volatile memory is the technology where we have the most collaboration within the consortium because almost all partners are involved in the development of these technologies. RF component, indeed, FD-SOI is quite well suited for RF and analog and mixed signal circuits. There again, allowing some power savings and covering a wide frequency range. So we are working on both active and passive components to couple to the FD-SOI CMOS technology. And then I will show a slide with the results of the past year, especially on RF switches, acoustic filters, and circulators. For 3D, we have 2 ways of developing 3D integration. First way is a sequential integration, meaning that we do a second process on top of the first one at low temperature to keep the performance of the first process. So it's what we call sequential integration to increase the complexity of circuit by putting a circuit on top of the other. And we especially try and assess the opportunity of this technology for GaN, microLED, and RF applications today. And we have another way of doing heterogeneous integration, 3D integration by, another way of doing 3D integration by heterogeneous integration. That means interconnection, silicon vias, and some manufacturing method like direct self-assembly approach to connect chips on wafers or die to wafers or wafers to wafers. and the idea is to increase the density of interconnection. And then on the last topic on integrated magnetics for power management in system on chips. So this is a part that is developed mainly between CEA-Leti and Tyndall in Ireland to develop components and integration of passive components very close to the system on chip. And especially by developing integrated magnetics with a way to manufacture them collectively by microtransfer printing. This is a technology, a technique that has been particularly developed by Tyndall. And in CEA, we have another task within this work package on 3D caps by developing high-density capacitors on 300 millimeter wafers, especially targeting 6G applications. And after 1 year, because the pilot line already has been implemented for 1 year, we have a number of results already. So first, it's a huge effort to increase the research capability by we built a new clean room. Actually, we started before the FAMES project, so that's why we can also have a delivery of the new clean room in a timely manner. Just a few months after the start of the project, we will inaugurate the clean room in October this year, which is very effective because we don't have to wait 2 or 3 years for the new clean room to come and then be already very far in the project. But it's a huge effort for all the teams to install the new equipment. Altogether, it's something like 80 or 90 new equipment that will arrive in the CEA-Leti clean rooms environment. On FD-SOI, we already have some first evaluation ready for the first 10 nanometer process. We have the design rule ready, first kit of design rule ready, and the first JDS is ready for tape out by the end of the year. So we already offer some insights, preliminary insights on our results on FD-SOI, 10 nanometers. Non-volatile memory. So we tested a bit first cell on Oxram. We have a test vehicle characterized for ferro RAM, and it was actually presented at IEDM last year. And we also develop thin film material like MOS2, and we've demonstrated the growth of this material at wafer scale. On RF component, we actually made a first optical actuation of a phase change material RF switch. We develop filters for 3 lithium niobate filters and FR3 and FR21 bands circulator designs also. 3D integration. So we continue the roadmap to increase high density integration below 5 nanometer of alignment with a sequential process. And we also develop new flavors, new types of TSV processes for heterogeneous integration. And then, as I said, the work package on eco-innovation and sustainable semiconductor manufacturing is also making good progress, especially on the LCA methodology, and trying to put in place a tool, the eScore tool, to use environmental KPI in the design of new process. And a huge effort in this work package is to collect data, to collect clean data from a clean room environment. So the access to the FAMES pilot line. The FAMES pilot line is open to all types of users. It could be large companies, SMEs, startups, research labs, different kind of companies. We have a process Oh, sorry. Yeah, that's not the right order. Okay. We have two ways to access the FAMES pilot line. We have yearly open access calls. Every year from March to May, we will open these calls with a list of technologies that are ready to use or ready uh, to 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 be used by potential users. And all along the year, we can receive spontaneous requests from any kind of user. So what is open in the FAMES pilot line? Um, the idea that the users could gain access to PDKs, some leading to silicon through multi-project wafers, or some others for evaluation from design assessment. Could access all the results of the FAMES technologies. It could be specific process steps or full module integration flows in all the technologies developed within FAMES, FD-SOI, but also memories, RF components, or 3D integration or power management ICs. And we will develop also education and training programs for designers, for companies, for technologies who would like to get trained on FD-SOI technology. And all these results are available as they are completed within the research program of FAMES. Especially for the research community, it could be interesting to leverage the PDKs to work with the students or PhD students or research team to create innovative IPs. And that could lead, we hope so in the end, to generate new fabless startups in Europe. That is somehow one of the weak points of Europe. And we need to help or support the emergence of new startups, new fabless in Europe. It's important for us because we are very eager to have some collaboration set up around the usage of these PDKs, because we need to get feedback on the first PDK releases to improve the following releases. And our aim is also to grow the community of researchers trained on FD-SOI, and especially try and provide incentive for younger researchers to get an interest into these technologies. So as I said, we have yearly open calls, and the first call was open from March to May in 25. And as a result, and this all goes with competence center and design centers. And the first results of the call we had in 25, we get a number of requests on all the technologies, as you can see, mainly to use the PDK, but also on 3-day training and MPWs related to memories. Type of users, as you see it, comes from academics, universities, SMEs, or startups. You don't see the large companies in this because they actually didn't use the open access call. They just send us a direct request using the spontaneous request mode, and they didn't really fill in the template during the open access call. But we have a number of discussions with large companies, but they prefer to do it directly with us because most of the time they already know us. And the origin of the user request, as you can see, is mainly Europe so far, which is very good to please the DG Connect that the pilot line is mainly so far leveraging interest within the European entity, because that's very important for us to look into the impact of the pilot line on the EU environment, let's say. And the second part, the second way to access the pilot line is through spontaneous request, as I said. So you can visit the website, the FAMES Pilot EU website. You will have you have a dedicated open access page when you can find the contacts, who to contact to make a request. But very important also in the technology section, you can see all the results, latest results of the pilot line. And we also have a LinkedIn. And I recommend that you could register to the LinkedIn page to follow the page, because we are now delivering posts about results on all technologies as they come available. And that's 20 minutes, so that's good, but it's just to open the discussion for question. So just all the partners and the funding agencies, because we have national, regional funding agencies. As you know, the pilot line is co-funded by EU, but also by all member states. And just as a teaser, because we started to discuss CHIPS Act 2, so maybe I will be back in some months to discuss about the new initiative we are launching now, the Resolve project, to aiming to gain a factor of 1,000 on the energy efficiency. That's only one slide. I won't say more, but we are preparing the revision of the CHIPS Act and the next, let's say, generation of project for CHIPS Act 2, and we believe we have to go further. And that's it for me.